All right, guys, welcome to class for Monday. We're going to wrap up the aerobic adaptations to endurance training notes here. And we finished up talking about VO2 max and AVO2 difference changes. Now we're going to move up to the top part of this graph, which looks more at lactate threshold changes and performance VO2 changes. So let's talk about that a little bit. So let's look at performance VO2 and substrate utilization, okay? What we see here with these couple graphs is we see energy from carbohydrate usage right here, energy from fat usage right here. We see that before training versus after training, we use a little bit less energy from carbohydrates after training. And then you could guess that this would flip-flop on the fat side, right? We use a little bit more energy from carbohydrate or from fat, okay? Why is this advantageous? Because it saves glycogen, okay, which decreases fatigue. Okay, if we're using fat, saves glycogen, decreases fatigue. Fat storage is, for the most part, infinite. For all practical purposes, we have as much fat to use as we want. Okay, how does this happen? This happens by increased mitochondrial power, right? Also increased fat storage in muscle, overall increased oxidative capacity. All those other things we talked about that help us get oxygen to the muscle, like myoglobin, capillaries, all those things. All of that helps us, right? Because this allows us to use our oxidative system more, which fat is the oxidative system is the only place that fat can be burnt. So this is a good thing overall, okay? But how is this connected to our hormonal system or our neuroendocrine system with SNS activity, okay? What we see here is fat percentage utilization, carbohydrate percentage utilization, carbs are in blue, fats are in the dashed red line, okay? So with training, we, for a given amount of aerobic power, right here, right, training pushes this relationship this way, which pretty much means that we burn less carbohydrates at any given intensity and more fat at any given intensity, like we just talked about. And this is directly connected to our sympathetic nervous system stimulation. And we can see this when we look at the blood. We look at blood epinephrine levels and how they're related to blood lactate levels, and look at that relationship there. They're clearly connected to each other, right? So this idea back here of showing that we're using less carbs and more fat is directly connected to the exercise at a given intensity is easier for us, right? It's less stress on our body because we can keep up with it, keep up to get the amount of ATP we need with our oxidative system. So we have less stress, which means less epinephrine release, which means less anaerobic system usage and less blood lactate production. And this is going to be directly connected to lactate threshold, right? So substrate utilization changes and SNS activation changes relate to the lactate threshold. Well, just like this. So before training, lactate threshold occurred around 55% of max, okay? After training, we see that lactate threshold occurring somewhere around 78% of max, right? That's a huge shift, okay? Why is that? Well, it's because of increased oxidative power. All right, so all those things, all factors mentioned for the increased AVO2 difference, those are the ones that cause this too, right? Those are the ones that cause this. Anything that lets us use our oxidative system more, so our myoglobin increase, our capillary density increase, our mitochondrial density increase, our switching of fibers to more oxidative ones, or hypertrophy of type 1 fibers, all of those are going to allow us to use our oxidative system more into higher intensities of exercise, which means we use our glycolytic system less, which means we produce less lactate at a given intensity, which means we're not going to max out our ability to deal with that lactate, okay? But that's all on the lactate production side, okay? So all of these factors are going to decrease lactate production, right? But we also also, we can increase lactate clearance. Okay, we can increase lactate clearance by increased lactate shuttles. And we can increase circulation. That helps us circulate lactate around, get it out quicker, okay? And lastly, we can increase our buffering capacity in the blood. Okay, that doesn't necessarily help with the lactate, but that helps with the hydrogen ion that's released, okay? So if we have a decrease in lactate production, increase in lactate clearance, that results in an increase in lactate threshold. And that's really what these graphs get at right here, okay? So this one shows at rate of appearance of lactate, and RA is rate of appearance and pre and post, and they have rate of disappearance pre and post, okay? So this one is looking at production. This one is looking at clearance. Okay, remember lactate threshold is the point that occurs when lactate production exceeds lactate clearance. Okay, so if we can decrease production and increase clearance, that's the recipe for increased lactate threshold. Okay, so let's look at rate of appearance pre versus post, right? So all of our, so resting is about the same, real low intensity exercise is about the same, but then once we start getting into a little bit more intense exercise, we see a decrease in appearance, right? Decrease in appearance, decrease in appearance, all through our submaximal levels. So production submaximally decreases. But then we got something interesting going on here, right? At max production increases, okay? So all the way throughout, we have less production because we can use our oxidative system more effectively, so we have to use our anaerobic system less, and we're better at clearing it, okay? But when we get to max, now all of a sudden we're making more lactate and there's more appearing, right? So maximal levels of lactate appearance are higher because our body can deal with that higher amount of stress and, oops, sorry about that, you don't want it upside down. So let's talk about this one. So maximal increases because body can deal with more stress. Okay, just get used to dealing with that stress, okay, before fatigue occurs, and we increase anaerobic enzyme capacity. Right, if we increase those anaerobic enzymes, then we're going to be able to make more lactate. Okay, what about the clearance side of things? It looks the opposite, right? We actually see rate of disappearance post is less. Well, it's really the same, but you would expect disappearance maybe to be higher. Well, it's totally tied to this, right? If there's less appearing, then there's going to be less to disappear, right? Until we get out here to maximal. Okay, so submaximal equals decreased, but maximal is increased, right? So one of the reasons we can have more appearance is because we're better at clearing it too, right? So we're better at clearing it. Those same reasons I mentioned back on this slide, right? Increased lactate shuttles, increased lactate shuttles, increased circulation, and increased buffering capacity. So those are important reasons why our lactate threshold increases, okay? And this just kind of shows that. So overall, that decreased appearance is going to be linked to this decreased epinephrine levels. Okay, like I mentioned before, increase in lactate shuttle is going to help with the removal part. Okay, so then let's translate that to actual running speed, right? How do we actually run faster? Okay, so how do these changes in substrate utilization and lactate threshold translate to changes in running pace or maximal sustainable intensity? Okay, if we look at two athletes here, or so one athlete that changed their intensity with training, their VO2 max didn't change, okay? So this can happen if you have somebody who's already highly trained, they've been training for a long time, they increase their workouts, their VO2 max most likely won't change at that point, okay? Because they've already trained so much, but they can expect or hope to expect to be able to use a higher percentage of their VO2 max. And that this is the change we would expect to see. Maybe their maximal sustainable intensity was only about 75% of max before training. We would hope to move that up to 88% of max after training. And so that's a huge difference. Dang it, sorry. Almost a 10 milliliter increase in maximal sustainable VO2. That translates to about a 2.5 kilometer per hour difference in velocity, and that's huge, right? So that's really what the key change is here. Okay, so summarize this. Lactate threshold increase, how does this help? So obviously increases, how does it help? Because it increases max sustainable intensity. Okay, what would happen to our RAR? Submaximally, RAR would go down, right? What this means is increased fat usage, decreased carb usage. Okay, but maximal RAR is actually going to go up. What this means is increased glycolytic system usage and increased ability to deal with stress. Okay, what about oxygen uptake? Well, our submaximal VO2, we don't expect much of a change. Okay, if anything, maybe down slightly. What that would mean would be increased economy, right? To run at 6 miles per hour, it takes you less calories than it did before training. Okay, so that would save a little energy, but not much. It's very small. Okay, but maximal, we hope that VO2 max would go up some, but if it doesn't, we can still have improvements in running speed because of this increase in lactate threshold and maximal sustainable intensity. All right, let's talk a little bit about anaerobic adaptations. So anaerobic power, sprint performance, glycolytic enzymes, creatine phosphate enzymes, and fiber type changes in hypertrophy. Okay, so let's talk about anaerobic power first. We'll do something like a Wingate test. What we want to look at with anaerobic power is the first few seconds of sprinting. Okay, so just a 10 or 15 second sprint. We can see improvements in that by about 25% if we're lucky. Some of the studies don't show much. Some of them show about a 25% improvement. So that can change some, okay? What do those anaerobic power changes due to? Well, they're most likely due to hypertrophy of our type 2 fibers and some shifting of our type 1 fibers to be type 2 fibers, okay? So we got more bigger fibers that can produce a lot more force. Okay, what about changes in the creatine phosphate system? We would expect that to be part of this because we say anaerobic power is a measurement of that. Okay, so creatine kinase activity can be increased modestly with training, but how much? Maybe only about 15%. So that's the main enzyme running the creatine phosphate system. That's CK right here. Okay, there was this kind of study that your book talks about where they had people do 6-second sprints in one group, and then the other group did 30-second sprints. They expected the 6-second sprint group to improve their creatine phosphate activity more than the 30-second group, because that's supposed to be what really taxes the creatine phosphate system. But what they saw was the opposite. We see greater increase in creatine kinase and myokinase enzyme activity, which is also part of this creatine phosphate system. We see the greater increase with the 30-second sprints instead of the 6-second sprints. But there have been some follow-up studies that have shown increases with just a 5-second sprint too. So, yeah. But the interesting part about the study was their performance improvements between the 6-second sprint group and the 30-second sprint group actually showed about the same. Okay, this was their maximal knee extension time. This is like a fatigue measurement. They just do maximal knee extensions as long as they can. Okay, and their time post training, if we look at the blue dots, goes down a little bit, right? Or sorry, goes up a little bit. So they can actually they actually warded off fatigue, and they did that the same whether they're in the 6-second group or the 30-second group. Okay, so enzyme improvement was only in the 30-second group, not the 6-second group, but the performance improvement was the same in both. So what does that tell you? It tells you that the creatine kinase and myokinase activity is not the deciding factor on performance here. Okay, what about other enzymes? Okay, we've already talked about the aerobic enzymes with training, But what about anaerobic enzymes? Okay, we talked about these some. So we look at creatine kinase, myokinase, we saw those. We see untrained versus anaerobically trained. So those definitely go up. Okay, this would be like lots of sprint type activity. Okay, what about these other important glycolytic enzymes like phosphofructokinase, lactate dehydrogenase, phosphorylase, phosphofructokinase? All these are important glycolytic enzymes, right? We see increases in all of these with anaerobic training and not so much with aerobic training. Okay, so the body is specific again here. With anaerobic training, we get anaerobic enzyme activity increases and not so much with aerobic training. We can expect to see somewhere around 10 to 50%. So not as great as what we see with the oxidative enzymes. What about HIT in improving these? Okay, HIT, the way we need to define it is a heart rate of 85 to 95% of max for your on time, okay, and then a recovery period, and then back to on again. Most common ones in the research are this, a 4x4 versus a 10x1. So 4x4 is 4 minutes on and 3 minutes off. You do that 4 times. 10x1 is 1 minute off, 1 minute off, 10 times back and forth. Okay, repeat 10 times, not 1 time. So we see HIT versus just regular endurance training with COX enzyme activity. That's an electron transport chain enzyme. HIT improves it quite a bit, similar amount, maybe, yeah, probably a similar amount to normal endurance training, but then how does that improve our cycling performance? Okay, cycling performance, I actually see endurance improvements a little bit better in the HIT, but also somewhat similar. Bottom line is we can do this with HIT with much less time commitment to the training. All right, guys, that's all we got for this. We'll be back again on Wednesday with the start of the heat, adaptations to heat, and then we'll come back for a synchronous session after that. All right, see you guys.